To solve a problem with the isochoric process. So, a car cylinder piston is filled with air at standard temperature and pressure and has a volume of 500 cubic centimeter. It is being pushed down and shrunk at 50 cubic centimeter and heat up with the initial temperature of 600 Kelvin and final temperature of 925 Kelvin. We're asked to find the work done by the piston, heat added to the gas, change in the internal energy, and the initial and final pressure of the cylinder piston. So first, we're gonna discuss the isochoric process. Isochoric process means the volume is constant and the work done by the system is equals to 0. So first, we're gonna draw a diagram that define the problem. So, a car cylinder piston, assume that this is a car cylinder piston with an volume of 500 cubic centimeter, is filled with air at standard temperature and pressure. At standard temperature and pressure, is being pushed down and shrunk at 50 cubic centimeter. It is being pushed down at 50 cubic centimeter. Since this is an isochoric process, the volume is constant, so the initial and final must be equal. 50 cubic centimeter. And the given is, it is being heat up, assuming this is the heat up with an initial temperature of 600 Kelvin and a final temperature of 925 Kelvin. So first, we're gonna identify our formula, which is PV is equals to nRT, and change internal energy is equals to heat minus work. So the first problem we're gonna solve is work done by the piston, heat added to the gas, and change in internal energy. Since our problem is an isochoric process, the work done by the system is equals to 0. So change internal energy is equals to heat minus work. The work is equals to 0, so we cancel out, and the change in internal energy is equals to heat. Since change in internal energy is equals to NCB is equals to change in temperature, so they both equal, so the heat also is equals to NCB, change in temperature. So we're asked to find the heat added to the gas, and we are now solving for the mole of the air inside. So first, we're gonna identify the problem. So it's filled with air at standard temperature and pressure. So volume at standard temperature and pressure for 1 mole of gas is equals to 22.4 liters, and we're gonna change it into liter. 500 cubic centimeter is equals to 0.5 liters. So we're asked to find the mole of the gas inside. So we're gonna solve this fractional part. 0.5 liters divided by 22.4 liters is equals to, we're gonna use our calculator. 0.5 divided by 22.4 is equals to 0.5 22.4 is equals to 0.0223 liters. Oh no, that's wrong. Mole. So our given, we have an given of a mole, so we can solve it. Q is equals to 0.0223 mole. Specific heat in the air is equals to 5 half R multiplied by the change in temperature final minus initial 925 Kelvin minus 600 Kelvin. So heat is equals to 0.0223 mole 5 multiplied by 5 half. The value of R is equals to 8.315 joule per mole times Kelvin. 8.315 joule per mole Kelvin. The difference between the final and the initial is 325 Kelvin. I'm gonna solve this. 0.0223 multiplied by 5 half times 8.315 multiplied by 325 Kelvin is equals to, oh, that's big. So our change in, so our heat is equals to, heat produced is equals to 150.66 joule. So heat is equals to change in internal energy. So our change in internal energy is equal to 150.66 joule. So we have solved 3 questions: work done by the piston, heat added to the gas, and change in internal energy. Finally, we are trying to solve the initial and final pressure of the cylinder piston. We're asked to find the initial and final pressure of the cylinder piston. So first, gonna equate this. P is equals to nRT divided by V. So pressure is equals to N. Since we are trying to solve the initial pressure, so initial pressure is equals to NR, initial temperature, divided by the volume. So we have an value for the mole, which is 0.0223 mole divided by, I multiply by 8.315 joule per mole Kelvin, mole per Kelvin, and the initial temperature is 600 Kelvin, and the initial volume is equals to 50. Oh, we must change the cubic centimeter to cubic meter. So a 1 meter is equals to 100 cubic centimeter. So we're gonna cube this, and it's equals to 1 million. So we're gonna move the decimal places 6 times. 1, 2, 3, 4, 5. No, 5, 6 cubic meter. So we're gonna compute this. 0.0223 multiplied by 8.315 multiplied by 600 divided by 0.0005 is equals to 22.23 times 10 to the 6 Newton per meter squared, and it's equivalent to 20 atmosphere. So we have an initial pressure, so we're gonna solve for the final pressure. Final pressure is equals to nRT over V. So we have an given mole of 0.0223 mole multiplied by R, which is 8.315 joule per mole Kelvin, multiplied by final temperature, which is 925 Kelvin, over by the final volume is 50 cubic centimeter. In cubic meter is equals to 0.000050 cubic meter. So we're gonna solve this. We're going to change the value 925. So the answer is 3.43 times 10 to the 6 Newton meter squared. It's equivalent to 34 atmosphere. So finally, we have now the value for the initial and final pressure. So at initial pressure, the value is 20 atmosphere, and it is lift up and is going up at 34 atmosphere. So it is enough to lift an car going up. So yun na.